Hi, my name is Yara Ayad, a PhD student in the University of Liverpool. Today I'm going to present my paper on the effect of street grid form on urban wind flow and pedestrian thermal comfort. The recent growth has led to a large increase in the world's population. With this in mind, most people live in the cities, creating problems of overcrowding, pollution, and poor outdoor urban environments. Better informed and more sustainable planning might help improve the comfort conditions in these urban environments. This study explores how different street grid systems, as a single aspect of urban layout, can affect wind flow and the thermal stress. The thermal index used in this study is the physiological equivalent temperature PET. It was used to assess the effect of urban microclimatic factors on the human body. This index takes into consideration the human and environmental factors. This included mean radiant temperature and the metabolic rate. To assess the urban layouts, EnviMet was used to simulate different scenarios. EnviMet is a three-dimensional software that models the interactions between the urban microclimate and the local built environment. 4 layouts were designed on a 150 by 150 meter plot. Using EnviMet, the scenarios were modeled into 2 orientations, a north orientation and a 45-degree angle rotation of north. The output data were extracted from 2 receptors at a human height of 1.75 meters. For layout A1, the approaching wind creates a helical flow inside the plot. This raises the average wind speed for the entirety of the layout. In A2, the approaching wind enters the plot from the west. This creates a channeling flow inside the west-east oriented streets, which increases the wind speed in these set streets, but lowers the overall wind speed for the layout. This slide shows the distribution of wind speed inside the 2 layouts. Scenario A2 shows a higher percentage of low wind speed compared to scenario A1. The PET values reflect the time the receptors have been exposed to direct solar radiation. The change of orientation of the plot changed the areas that the sun would reach in different times of the day. And when inspecting the shadows casted by the buildings for both of the scenarios, it was concluded that scenario A1 have the least time duration of direct sun radiation. As in A1 layout, a helical flow is generated in B1 scenario. However, the central attached building hinders the flow where it gathers in the west-east oriented streets and exits from the north-south oriented streets. In B2, the channeling flow is stronger and wind speed is very low in the north-south oriented streets. The wind distribution for B2 shows a high percentage of low wind speed when compared to B1. This is due to the effect of the channeling flow in the west-east oriented streets. The PET values for the receptors show similar trends due to the similarity in conditions in both locations. Scenario B2 shows higher PET values in the morning and late afternoon due to its orientation, while B1 have higher midday values. The radial configuration showed to have poor wind speed values due to the complexity of the geometry, where the average wind speed ranged between 0.1 to 1.25 meter per second. The wind distribution chart showed a high percentage for low wind speed in both scenarios for the radial grid system. Scenario D1 have lower PET values than scenario D2. This is due to its location being on the west-east axis, where direct sunlight reaches the receptors in the early morning and evening. The street grid analysis showed interesting results throughout the different layouts. Wind speed was affected greatly by the change of orientation, where the 45-degree rotation from north showed a major improvement in wind flow distribution. However, the change in orientation did not play a key part in the PET levels, even though the change in orientation changed the shadow patterns. The main reason behind the rise and fall of PET levels was the geometry of the plot, whether it was rotated from the original orientation or not. Understanding the geometry of the site is a key component in determining the thermal stress of the human body. In Table 1, scenarios 1 with 45-degree orientation of north showed improved results when compared to Scenario 2. Layout A1 showed better results across all layouts, with only 6% of the area having low wind speed between 0 and 0.5 meters per second, while Layout D showed the worst results across the layouts due to its curved streets that obstructed wind flow, with 68% of the area having low wind speed. The average PET values showed in Table 2 do not convey how well the layouts represent their comfort level, but rather they show how in the same layout the different orientation shift the comfort level. An increase in PET levels is noticed in all of the layouts in Scenarios 2. This is caused by the north-south orientation streets that receive the highest sun radiation throughout the day. Thank you so much for listening, and I hope you have a great day.